You have felt an electron move. The small snap when you touch a metal doorknob in winter is electrons jumping a gap, and the warm phone in your hand is electrons pushing through it, carrying energy from one place to another. The electron inside an atom has been moving since that atom formed, often billions of years ago, and it has never slowed down, never run out, and nothing has ever come along to refill it. That fact nearly broke physics 100 years ago. The question is simple to ask. Where does an electron get its energy from? We're going to build the answer slowly, one plain step at a time, starting from things you already know. If you enjoy the calm and the wonder here, take a moment to subscribe and stay with me. We can begin with one small, honest question. Why doesn't the electron simply fall into the center of the atom? Reach out and touch a metal doorknob on a dry winter morning, and sometimes a tiny spark jumps the last small gap between your skin and the metal. You feel it as a quick, sharp snap. That snap is a crowd of electrons leaping across the air, and for a fraction of a second you have watched with your own nerves the same particle that runs every machine you own. The light you're reading by is electrons being shaken inside a screen. The sound near you is electrons pushed back and forth through copper to move a speaker cone. Electrons are not rare, and they are not far away. They are the busiest thing in your house, and you have lived your whole life surrounded by them without once seeing one. Let me give you a sense of how many there are. In a single copper penny there are roughly as many electrons as there are grains of sand on every beach on Earth, many times over. They fill the metal completely, packed into every atom, and in a wire they drift along like water easing through a crowded hallway. When you switch on a lamp, you're not sending fresh electrons down the wire from the power station. The electrons are already there, sitting in the copper, waiting. The switch simply gives them a gentle, steady push, and the whole crowd shifts together, and the room fills with light. Here is the thing worth pausing on. Every one of those electrons carries energy, and it has been carrying that energy for a very long time. The electrons in the copper of that penny were forged inside stars and scattered across space before the Earth existed. They have been moving the entire time. They moved while the planet cooled, while the oceans formed, while every living thing that ever breathed came and went. And in all that time, no electron in that penny has ever slowed to a stop and stayed there. None has run dry. None has needed refilling. You know from ordinary life that moving things slow down. A spinning top wobbles and falls, a rolling ball comes to rest, a swing you stop pushing settles back to hanging still. Motion costs something, and when the pushing stops, the motion fades. This is one of the most reliable facts you carry, learned before you could name it, confirmed every single day. And yet the electron inside an atom breaks it completely. It moves and never settles, with no one pushing, for billions of years. That is the puzzle this whole script is built to answer. The question is short. Where does an electron get its energy from? It sounds almost too simple, the kind of thing a child asks at dinner, and the adult says the electron just has energy, and the conversation moves on. But the honest answer took the sharpest minds of the 20th century more than 30 years to reach, and along the way it forced them to rebuild the idea of an atom from nothing, twice. The answer is one of the strangest and most beautiful things we know, and you can understand all of it. We're going to get there slowly. We will start with the electron you already know, the one in the doorknob and the wire, and we will follow it inward, down into the atom, until the ordinary picture stops working. Then we will rebuild it, piece by piece, the way the physicists actually did, with the experiments that forced each step. By the end, the snap of that winter spark will mean something different to you. You will know what the electron is doing in there and why it never stops. So let us begin where the trouble first started, with a deceptively simple problem. To find an electron's energy, we first had to find the electron itself, and that turned out to be the harder task. For most of human history, no one believed the electron existed because no one could see it, weigh it, or hold it. The idea that matter might come in tiny indivisible pieces was old, going back to thinkers in ancient Greece who guessed the world was built from atoms. But guessing is not knowing, and for 2,000 years it stayed a guess. The man who turned the guess into a measured fact was an English physicist named Joseph John Thomson, known to everyone as JJ, who worked at the Cavendish Laboratory in Cambridge in the 1890s. He was famously clumsy with his hands, so awkward in the lab that his assistants quietly steered him away from the delicate glassware, and yet his mind built the most delicate experiments of the age. Thomson was studying a strange glow. If you take a sealed glass tube, pump most of the air out, and run a high voltage across two metal plates inside it, a faint ray streams from the negative plate to the positive one. These were called cathode rays, and no one agreed what they were. Some thought they were a kind of light. Others thought they were charged particles. The rays were invisible, but they made the glass glow where they struck, so you could see where they landed even though you could not see them travel. Thomson did something clever. He treated the invisible ray as if it were a tiny ball he could push around. He put electric plates above and below the ray and watched it bend toward the positive plate, which told him the ray was made of something carrying negative charge. Then he added a magnet, which bends a moving charge a different way, and by balancing the electric push against the magnetic push, he could work out how fast the particles flew and how much they bent. From that bending, he pulled out a single number, the ratio of the particle's charge to its mass, and the number was a shock. Whatever these particles were, they were almost 2,000 times lighter than a hydrogen atom, the lightest atom known. Until that moment, the atom was thought to be the smallest thing there was, the floor of matter. Thomson had found something smaller, a piece that came from inside the atom. He had broken the unbreakable. Think of how you might weigh something you cannot see by watching how easily a breeze moves it. A feather lifts on the faintest puff of air, while a stone in the same breeze does not stir. The amount of bending and a steady push tells you how heavy the thing is, even with your eyes closed. Thomson's breeze was an electric field, and the cathode ray bent so easily that the thing being pushed had to be extraordinarily light. He could not see the particle, but he could see how the push moved it, and that was enough. He announced his result in 1897, and at first many scientists simply did not believe him. The claim was enormous. He was saying that inside every atom of every element sat the same tiny negative particle, identical from gold to glass to the air in the room. He called these particles corpuscles, though the name electron, coined earlier by another physicist, soon won out. For this work, Thomson later received the Nobel Prize, and in a fitting turn, his own son George went on to win a Nobel Prize of his own, for showing that the electron also behaves like a wave, a twist we will reach later. So now we have our particle, named and measured. It is real, it is part of every atom, and it is astonishingly light. But knowing it exists is not the same as knowing how small and how light it truly is. Those numbers are hard to feel, and we should sit with them before we go further, because the smallness of the electron is the first key to its strangeness. The electron is so light that ordinary words for weight stop meaning anything. Its mass is about 9 times 10 to the minus 31 kilograms. Written out, that is a decimal point followed by 30 zeros and then a 9. There is no scale in your kitchen, no scale anywhere on Earth, that could register a single electron, and there never could be, because the number is far below anything we build instruments to touch. Let me try to give that number a body you can hold. Imagine you wanted to gather enough electrons to equal the weight of a single grain of salt. A grain of salt is already small, barely a speck you could lose in the lines of your palm. To match it, you would need to collect roughly 1,000 trillion electrons. If you started counting them, one each second, you would not finish in the lifetime of the universe. You would not come close. The salt grain sits quietly on your fingertip, and inside its weight hides a number larger than every second that has passed since time began. The electron is also small in size, though here we have to be careful, because size for an electron is a slippery idea we will return to. As far as every experiment can tell, the electron has no size at all. It behaves like a true point, a place with no width, no surface, no inside. We have probed it with our most powerful machines, slamming electrons together at nearly the speed of light to see if they have any structure, any seam where they might split. They never do. The electron appears to be one of the few things in nature that is genuinely fundamental, not made of smaller parts, a particle with nothing underneath it. Now set its weight aside and look at the other thing it carries, its charge. Every electron holds exactly the same amount of negative electric charge, and that amount is a fixed unit of nature, the same for every electron that has ever existed. You cannot have half of it. You cannot have 1 1/3. Charge comes in whole electrons, the way eggs come in whole eggs, never a fraction left over in the carton. This wholeness is one of the deepest and most reliable facts in all of physics, true to a precision finer than almost anything else we measure. That single unit of charge is what makes the electron useful and what makes it matter. The charge is why it feels the pull of the positive nucleus at the center of the atom. The charge is why it can be pushed through a wire by a battery. The charge is why the winter spark jumps the gap to your hand. Strip the charge away, and the electron would drift through the world untouched and untouching, felt by nothing. It is the charge that ties the electron into everything else. So picture it now as clearly as you can. A particle with no size, lighter than almost anything has a right to be, carrying one fixed whole unit of negative charge and never wearing out. That is the thing we are chasing. And the question we asked at the start, where its energy comes from, now sharpens. A point with almost no mass, holding its motion for billions of years, refusing to stop. Before we can ask where its energy comes from, we should be honest about a word we have been using freely, as if its meaning were obvious. We keep saying energy. We had better be sure we know what that word actually means, because the whole answer turns on it. Energy is one of those words everyone uses and almost no one can define, and that is not your fault, because for a long time the physicists could not define it either. We say a strong coffee gives us energy, that a storm has a lot of energy, that a tired child has run out of it. These uses point at something real, but they blur it. To follow the electron, we need the word sharpened down to its physical bones, and the physical meaning turns out to be simpler and stranger than the everyday one. In physics, energy comes in 2 great families, and almost everything else is a variation on these 2. The first is the energy of motion, called kinetic energy. A thrown ball has it, a running river has it. The faster a thing moves and the more massive it is, the more energy of motion it carries. You feel this directly. A tennis ball tossed gently you can catch with a soft hand. The same ball fired from a machine stings your palm because it arrives with far more energy of motion, and that energy has to go somewhere when it stops, into the sting in your skin. The second family is the energy of position, called potential energy. This is energy a thing holds simply because of where it sits, waiting, ready to turn into motion if released. A boulder at the top of a hill has it. The boulder is not moving, yet it holds the promise of all the motion it would gain rolling down. Lift a book from the floor to a high shelf, and you have stored energy in it, paid for by the effort of your arm. Let the book fall, and that stored energy of position becomes energy of motion on the way down, and then becomes a thud and a little warmth when it lands. Hold that pair in mind, motion and position, because the electron lives by both. And here is the rule that binds them, the rule that turns out to be the quiet hero of this entire story. Energy is never made and never destroyed. It only changes from one form into another. When the book falls, no new energy appears. The energy of position it had on the shelf simply converts, neatly and exactly, into the energy of motion it has when it hits the floor. The books on the shelf, the boulder on the hill, the coffee, the storm, everyone is energy moving between its forms, with the total always holding steady. This is the law of conservation of energy, and it was hard won. Through the 1840s, a German doctor named Julius Robert von Mayer working on ships in the tropics, and an English brewer's son named James Prescott Joule, measuring the faint warming of water churned by a paddle, came at the same truth from different directions. Joule was so devoted to measurement that the story goes he tried to measure the temperature of water at the top and bottom of a waterfall on his honeymoon. Their work established that heat and motion and stored position are all the same currency, energy, exchangeable but never lost. Keep that law close, because it is going to press on us hard. If energy is never made and never destroyed, then the electron inside the atom moving for billions of years cannot be making its own energy. It must have gotten that energy from somewhere, or it must have held it from the start. There is no third option that the law allows. The question is no longer loose or childish. It is a demand the deepest rule in physics places on us. Either we find the source, or we find the moment it was given, or something we believe is wrong. So let us go looking. To find where the electron's energy lives, we first have to go inside the atom and see where the electron actually sits. And the inside of the atom is far emptier and far stranger than anyone expected. In the years just after Thomson found the electron, the atom was pictured as a soft, comfortable thing. Thomson himself imagined it as a ball of positive charge with a tiny negative electron stuck inside it, like raisins in a pudding or seeds in a fruit. It was a reasonable guess. The atom was known to be neutral overall, so the negative electrons needed some positive charge to balance them, and spreading that positive charge through a soft ball seemed as good a way as any. For a few years, the pudding stood. It was destroyed by a New Zealand farmer's son named Ernest Rutherford, a big, loud, confident man with a booming voice that colleagues said could disturb sensitive instruments from across the building. Rutherford had an instinct for the decisive experiment, the single test that would force nature to answer plainly. Working in Manchester around 1909, he set two of his assistants, Hans Geiger and a young student named Ernest Marsden, to a careful task. They would fire tiny, fast, positively charged bullets, called alpha particles, at an extremely thin sheet of gold foil and watch where they went. The expectation was gentle. If the atom were a soft pudding of spread-out charge, the heavy alpha bullets should sail straight through the foil, barely nudged, like a fast stone passing through a bank of fog. And most of them did exactly that. They passed clean through the gold as if it were not there, which already tells you how empty the atom is. But Rutherford asked Marsden to look for the rare bullet that bounced back, almost as a matter of thoroughness, not expecting to find any. They found them. Once in a great while, an alpha particle struck the foil and came straight back the way it had come, as if it had hit something solid and immovable. Rutherford later said it was the most incredible event of his life, that it was as if you had fired a large shell at a sheet of tissue paper and the shell had bounced back and hit you. Something tiny inside the gold was hard enough and concentrated enough to turn a fast, heavy bullet completely around. From the rare bounces, Rutherford worked out the truth. The positive charge of the atom was not spread out softly at all. It was crammed into a minuscule, dense lump at the centre, which he named the nucleus. The nucleus held nearly all the atom's mass in a space unimaginably smaller than the atom itself, and the electron sat far out from it with vast emptiness in between. Let me give you that emptiness in a picture you can stand inside. Imagine the nucleus of an atom blown up to the size of a marble and set on the centre line of a large sports stadium. On that scale, the electrons would be tinier than grains of dust, drifting somewhere up in the higher seats around the stadium's outer rim. Everything between the marble at the centre and the dust in the high seats is empty. That is the atom. That is what you're made of, what the floor is made of, what feels so reassuringly solid under your feet. Almost all of it is nothing at all, so the solid world is a trick of forces across empty space, and the electron lives at the far edge of that emptiness, held to the distant nucleus by the pull between its negative charge and the nucleus's positive one. This gave the physicists a clean, simple, beautiful picture to work with. A tiny, heavy centre, a light electron circling far out, held by an attractive pull. It looked just like a planet orbiting the sun. It was elegant, it was intuitive, and as we are about to see, it could not possibly be true. The picture Rutherford handed the world was lovely, and you have almost certainly seen it. A small sun at the centre, the nucleus, and around it the electrons swinging in neat circles like planets, each on its own track. It hangs on classroom walls and rides on the badges of science. It feels right because it matches something you already understand, the solar system, where the sun's gravity holds the planets in their orbits and they circle for ages without falling in. Swap gravity for the electric pull between opposite charges, and the comparison seems to slot in perfectly. Let me honour that picture for a moment, because it gets several things right. The electron really is held to the nucleus by a pull, just as a planet is held to the sun. The pull really does weaken with distance in the same mathematical way for both. An electron far from the nucleus really is held more loosely, and one close in more tightly, just as the inner planets feel the sun's grip more strongly than the outer ones. For a moving electron to keep circling, it really does need to be held by that inward pull, balanced against its tendency to fly off straight. So far, the solar system works as a guide, and it is no surprise the early physicists embraced it. Now, let us find the place where the comparison cracks, because that crack is where the real physics begins. A planet circling the sun is held by gravity, and gravity is gentle in a particular way. It pulls the planet without ever forcing it to pour out its energy. The Earth has circled the sun for billions of years on roughly the same path, losing almost nothing because gravity simply holds it and asks for nothing in return. The orbit is stable, it can last for all practical purposes forever. But the electron is not held by gravity. It is held by the electric force, and the electron carries charge. And a charge is a very different kind of passenger than a planet. A planet circling the sun is just mass following a curve. A charge circling the nucleus is a charge being constantly turned, constantly changing its direction, and that turning is the problem. Here the calm planet picture and the truth begin to pull apart, and the gap between them is fatal. To see why, we have to look at what happens whenever a charge changes its motion, whenever it speeds up, slows down, or turns. This is a piece of physics that was already well understood in Rutherford's time, settled decades earlier, and it is ironclad. A charge that is forced to change its direction does not circle quietly the way a planet does. It pays a price, and the price is paid in light. This single fact, known and trusted long before anyone looked inside an atom, is what turns the pretty solar system atom into an impossibility. The early physicists knew this. They were not foolish, and they did not miss it. The men who drew the orbiting electron understood perfectly well that a charge moving in a circle should behave in a way that would wreck the orbit in an instant. They drew it anyway, because they had nothing better, and because the experiment plainly showed a tiny nucleus with electrons somewhere out beyond it. The picture was the best they could build from what they knew, and they could feel the flaw sitting inside it like a crack in a bell. So the atom that should explain the solid, lasting world had a hidden contradiction at its heart. The very thing that made the electron useful, its charge, was the thing that should have destroyed its orbit. To understand the size of the disaster, we need to look closely at that rule about moving charges and light. Once you see what an accelerating charge really does, you will see why the classical atom was doomed. There is a rule about charges that you already half know from everyday life, even if no one ever named it for you. Whenever an electric charge is shaken, sped up, slowed down, or turned, it throws off light. Not always visible light, but light in the broad sense, the rippling waves of electric and magnetic force that travel across space. A charge sitting still makes no light. A charge moving steadily in a straight line makes no light. But a charge that changes its motion, that accelerates in any way, always radiates. This was worked out in the 1860s by a Scottish physicist named James Clerk Maxwell. a quiet, deeply religious man who could do ferocious mathematics in his head and who wrote playful poems on the side. You meet this rule every day without knowing it. A radio antenna is nothing more than a rod with electrons driven up and down it, back and forth, millions of times each second. Each time those electrons reverse, they accelerate, and each acceleration flings out a ripple of electromagnetic waves, the radio waves that carry music and voices to your car, the light from the sun, the warmth from a heater, the signal to your phone. All of it is charges being shaken and shedding waves as they go. Maxwell's rule is not a fragile theory. It is the working principle behind nearly every device that sends a signal through the air. Here is the everyday handle. Think of a charge as a child sitting in the centre of a calm pond, holding the water still. As long as the child sits quietly, the surface stays smooth, no ripples spread. But the moment the child slaps the water or jerks a hand back and forth, ripples race outward across the whole pond, carrying energy away from the child to the distant banks. The charge is the hand, light is the ripple, and crucially, the ripple cost the child something. The energy in those spreading waves comes out of the child's own effort. Every ripple sent out is energy lost from the source. That last point is the one that matters for the atom. When a charge radiates light, the energy of that light does not come from nowhere. It is drained from the motion of the charge itself. A charge that radiates must slow down, must lose energy, must give up some of the very motion that was making the light. The pond cannot send ripples to the banks unless the hand spent energy stirring the water. Light carries energy outward, and that energy is always paid for by the thing that made it. Now bring this back to the orbiting electron and feel the trap close. An electron circling the nucleus is a charge that is constantly turning. It is never moving in a straight line, because a circle is a path that bends every instant. To go in a circle at all is to accelerate continuously, always being pulled inward, always changing direction. By Maxwell's rule, settled and certain, a charge that accelerates must radiate, and a charge that radiates must lose energy. The orbiting electron, simply by orbiting, by doing the one thing the solar system picture demands of it, should be pouring out light in a steady stream and bleeding away its energy with every turn. This is not a small leak. The electron in an atom whips around the nucleus at a furious rate, turning trillions upon trillions of times every second, and each turn is an acceleration, and each acceleration sheds light. The drain should be enormous, relentless, and immediate. And as the electron loses energy, it cannot keep its distance from the nucleus. Like a satellite losing speed, it must fall inward, spiraling closer and closer to the centre it can no longer resist. The pretty orbit is not stable at all. It is a slow leak that becomes a plunge. Let us follow that plunge to its end and see exactly how bad the news really is. Let us put real numbers on the catastrophe, because the size of it is the whole point. Take a single hydrogen atom, the simplest one there is, just one electron circling one proton. According to the settled physics of Maxwell, that orbiting electron should be radiating light continuously, losing energy continuously, and therefore spiraling inward continuously. The question is how fast? How long would the electron last before it crashed into the nucleus at the centre? The answer, when the physicist worked it out, was about 16 trillionths of a second. Not 16 years, not 16 seconds. 16 trillionths of 1 second, a span so short that light itself, the fastest thing there is, crosses only a fraction of a hair's width in that time. In that flicker, the classical electron should spiral down through tighter and tighter loops, radiating ever more fiercely as it falls, and slam into the nucleus, and the atom should simply cease to be. Sit with what that means. If the solar system atom were the true picture, then no atom could exist for longer than a heartbeat of a heartbeat. Every atom in the universe should have collapsed almost the instant it formed. There would be no stable matter, no chemistry, no molecules, no rocks, no water, no stars holding their shape, no you sitting here. The very fact that anything solid exists at all, that the world has lasted billions of years instead of trillionths of a second, stands as flat proof that the classical atom is wrong. Not slightly off, wrong at the root. This was the crisis, and it was a genuine one, not a small puzzle to be patched. The two great pillars of 19th century physics, Newton's mechanics and Maxwell's electricity, were each magnificent, tested 10,000 ways, trusted completely. Put them together and apply them to the atom, and they predicted instant collapse. The triumphs of classical physics, when aimed at the smallest thing, predicted that the smallest thing could not be. The more carefully you did the math with the best tools available, the worse the answer became. The trusted laws were not just failing quietly, they were screaming that the world should not exist. There is an everyday version of the feeling. Imagine you have a recipe you have used and trusted your whole life, one that has never failed, every ingredient measured, every step sound. You follow it perfectly one day, and the result is a flat, burnt ruin. You check the recipe again. The steps are right. The measurements are right. Everything you know says the cake should be perfect, and yet there it sits, inedible. At that point, you cannot blame the cook. You have to suspect that one of the rules you trusted, one of the steps you never questioned, is secretly false. That is exactly where physics stood. The atom on the table contradicted the recipe in their hands. So a real atom does something a charged particle circling a center has no classical right to do. It lasts. The electron holds its distance from the nucleus for billions of years, never spiraling in, never crashing, never radiating itself to death. Either Maxwell's iron rule about radiating charges somehow fails inside the atom, or Newton's mechanics fails there, or both do. Something that worked everywhere else breaks down completely at this scale, and the breakdown is total. The way out did not come from fixing the atom directly. It came from a different corner of physics entirely, from people studying glowing hot objects and the colours they give off. There, a few years earlier, a careful and conservative physicist had been forced into a strange idea he did not like and could not avoid. He found that energy, at the smallest scale, does not flow smoothly. It comes in lumps, and those lumps would turn out to be exactly what the dying atom needed. The clue that would save the atom came from an ordinary thing, the glow of hot objects. Heat a poker in a fire and it shifts from dull red to bright orange to a fierce yellow-white as it gets hotter. Every hot thing glows this way, and the exact mix of colours it gives off depends only on its temperature, not on what it is made of. In the 1890s, this everyday glow had become a stubborn scientific problem because the trusted physics of the day, applied to it, gave an answer that was not just wrong but absurd. The math predicted that any warm object should blaze with an infinite amount of high-frequency light, that every campfire should flood the room with a lethal burst of ultraviolet and worse. Since campfires plainly do not do this, something in the theory was broken. The man who cracked it was a German physicist named Max Planck, a careful, formal, deeply traditional man in his early 40s, the kind who wore a dark suit to his own lectures and respected the established laws as if they were sacred. He was the last person who would have wanted to overturn classical physics, and he spent weeks trying every respectable way to make the glow come out right. None worked. In a kind of desperation, in the year 1900 he tried a trick he frankly did not believe, purely because it made the numbers fit. Planck's trick was this. He supposed that the tiny charges inside the glowing object could not give off energy in any amount they liked, smoothly, in a continuous trickle. Instead, they could only release energy in discrete whole packets, little indivisible lumps. A charge could give off 1 lump, or 2 lumps, or 3, but never 1.5, never a smooth in between. Energy, at this scale, came in steps, like coins of a fixed value rather than a flowing liquid. He called each lump a quantum, from the Latin word for how much. The size of each lump was set by a new number Planck had to introduce, a constant of nature now written with the letter H and named for him, the Planck constant. It is a fantastically small number, around 6 times 10 to the minus 34 in the standard units, so small that in the everyday world the steps blur together and energy looks perfectly smooth, the way a sandy beach looks like a continuous surface until you bend close and see the separate grains. The lumpiness is always there. It is just far too fine for us to notice in daily life. Here is the everyday handle. Money comes in lumps. You can have 1 cent or 2 cents, but you cannot pay someone 4/10 of a cent, because the smallest coin sets the smallest step. Planck was saying that energy works the same way at the bottom. There is a smallest meaningful step set by his constant, and energy is always some whole number of those steps, never a fraction in between. For large amounts, like the dollars in a bank account, the single cent is too small to notice and money feels smooth. For the tiniest exchanges, the lump matters completely. With this strange rule, the glow problem dissolved. The lumpiness made it costly for the charges to give off high-frequency light, because high-frequency lumps are large, and that quietly shut off the absurd infinite blaze. Planck's formula matched the real glow of hot objects exactly, across every temperature and colour. He had the right answer. What troubled him for years afterward was that he did not believe his own assumption. He thought the lumps were a mathematical trick, a bookkeeping device, not a real feature of the world. He had found the first crack in the smooth classical picture, and he spent a long time hoping it was not real. It took a bolder mind to insist that the lumps were not a trick at all, but the truth. The bolder mind belonged to a 26-year-old clerk in a Swiss patent office, examining applications for electrical devices and doing physics in the hours between. His name was Albert Einstein, and in 1905, the same astonishing year in which he reshaped our ideas of space and time, he took Planck's reluctant lumps and did something Planck himself refused to do. He said the lumps were real. Energy did not just leave hot objects in packets as a quirk of the math. Light itself, Einstein argued, actually travels as packets, real and countable, each one a tiny grain of light. These grains would later be called photons. He did not pull this from thin air. He used it to solve another small, nagging mystery that the smooth picture of light could not explain, the photoelectric effect. The effect is simple to describe. Shine light on certain metals, and the light knocks electrons loose, kicking them right out of the surface. You can measure the freed electrons as a small electric current. It sounds harmless, and at first it seems like something the old wave picture of light should handle with ease. But the details were all wrong, and the wrongness was sharp and specific. If light were a smooth, continuous wave, as everyone believed, then brighter light should kick the electrons out harder, with more speed, because a brighter wave carries more energy and should shove the electron more forcefully, and dim light, given enough time, should slowly build up enough energy to free the electrons too. Both of these reasonable expectations were simply false. Dim blue light freed electrons instantly, while even a blazing, intense red light freed none at all, no matter how long it shone or how bright it was made. The colour of the light decided whether electrons came out. The brightness only decided how many. Einstein saw why, and the answer was the lump. If light arrives as individual packets, then each electron in the metal is freed by a single packet striking it, one on one, like one ball knocking one other ball loose. What matters is not how many packets arrive, but how much energy each single packet carries, and the energy of each packet depends on the light's colour, its frequency. Blue light comes in high-energy packets, each one carrying enough punch to knock an electron free in a single hit. Red light comes in low-energy packets, each too weak to free an electron no matter how many of them pile in. 1,000 gentle taps cannot do what one firm knock can. Here is the everyday handle. Imagine trying to dislodge a heavy rock that sits in a notch, needing one solid blow to pop it out. A crowd of children throwing soft foam balls at it, even hundreds of them, even all day long, will never move it, because no single foam ball hits hard enough. One adult with one firm strike pops it out at once. The foam balls are red light, many but each too weak. The single firm strike is blue light, one packet with enough energy to do the job. Brightness is the number of throwers, colour is the strength of each throw. Only the strength of each throw decides whether the rock comes free. This was the proof that the lump was real, not a bookkeeping trick. Light genuinely arrives in whole pieces, each carrying an energy set by Planck's constant times its frequency. Einstein received the Nobel Prize for this, not for relativity, and it remains one of the foundation stones of the new physics. The lesson lands hard for the atom. Energy at the small scale is not a smooth liquid, it comes in fixed pieces, and if light can only be given and taken in whole packets, then perhaps the electron in the atom can only hold and release energy in whole steps too. The next clue came written in coloured light, in the precise bright lines that glowing gases give off. If you take a tube of hydrogen gas, the simplest element, and run electricity through it so it glows, and then spread that light out through a prism, you do not get a smooth rainbow. You get something far stranger and more telling. Against a dark background, a few sharp, bright, separate lines of colour appear, and nothing in between. A particular red, a particular blue-green, a particular violet, each a thin, bright stripe at its own exact place, with darkness on either side. The gas does not give off all colours. It gives off only a handful, always the same handful, the same precise colours every time, like a fixed signature. This was known long before anyone could explain it, and every element has its own pattern, its own fixed set of bright lines, as distinct as a fingerprint. Sodium glows a specific yellow. Neon glows its particular red-orange in the signs over shop windows. Helium was actually discovered in the light of the sun, its unfamiliar lines spotted in sunlight before the element was ever found on Earth, which is why it carries the name of the Greek sun. These bright lines are how we know what distant stars are made of, reading their composition across the void by the exact colours they shine. The lines are nature's barcodes, and for decades no one knew why they existed. The lines of hydrogen were so clean that they begged to be understood. A Swiss school teacher named Johann Balmer, a man who taught mathematics to teenage girls and dabbled in numerical puzzles in his spare time, stared at the 4 visible hydrogen lines and, in 1885, in his 60s, found a simple formula that gave their exact positions. He had no idea why his formula worked. It was pure number matching, a pattern he noticed in the wavelengths, fitting them with small whole numbers in a tidy equation. But the fact that the colours followed a clean formula built from whole numbers was a thunderous hint. Whole numbers do not show up in nature for no reason. Connect this to what we have just learned, and the hint sharpens into a clue. Light comes in packets, and the energy of each packet is set by its colour. So when hydrogen gives off a sharp line of a particular colour, it is giving off packets of one particular energy. And it gives off only a few particular colours, which means it gives off only a few particular energies of light, and no others. The atom is choosy. It releases light of this energy and that energy, but never the energies in between. Something inside the atom only allows certain exact amounts of energy to come out. Here is the everyday handle. Think of a staircase against a ramp. On a ramp you can stop at any height you like, smoothly, anywhere along the slope. On a staircase, you can only stand on the steps, at fixed heights, and never in the gaps between them. If you drop a ball down a staircase, it can only fall from one step to another, and the drop is always some exact whole number of step heights, never a smooth in-between distance. The atom giving off only certain colours is behaving like a staircase, not a ramp. Its energy comes in fixed levels, and light is released only when the electron drops from one fixed level to another. That is the picture the spectral lines force upon us. The electron inside the atom cannot have just any energy. It is allowed only certain specific energies, certain rungs, and when it falls from a higher rung to a lower one, It gives off a packet of light whose colour is set by the exact size of that drop. The fixed colours are the fixed gaps between the rungs, made visible. The problem of why those rungs exist and where they come from is the next door we have to open, and the man who first pushed it open did so by simply forbidding the electron to do the thing that was killing it. The man who turned the spectral clue into a working atom was a young Danish physicist named Niels Bohr. Gentle, mumbling, endlessly thoughtful, a former goalkeeper on a Danish football team who thought so deeply and spoke so softly that listeners often had to lean in to catch him. In 1913, Bohr was working in England, having recently spent time in Rutherford's lab, and he carried in his head two facts that did not fit together. He had Rutherford's tiny nucleus with a distant electron, which classical physics said should collapse in an instant. And he had the sharp spectral lines and Planck's lumps, which said energy at this scale comes in fixed steps. Bohr's move was to force these two facts to live together by sheer decree. He made a bold and frankly outrageous assumption. He simply declared that the electron was allowed to circle the nucleus only in certain special orbits, at certain fixed distances, and nowhere in between. In those special orbits, and only there, the electron would not radiate light, would not lose energy, would not spiral inward, no matter what Maxwell's iron rule said. Bohr offered no reason why. He just asserted that in these chosen orbits the electron was stable, the collapse forbidden, the death spiral outlawed by fiat. It was less an explanation than a command laid on nature, and Bohr knew it. Then he added the second half. The electron could jump from one allowed orbit to another, and when it did, the difference in energy between the two orbits was carried away or taken on as a single packet of light, a photon, exactly in the manner Planck and Einstein had described. Drop from a high orbit to a low one, and the atom spits out a photon whose energy equals the gap. Climb from a low orbit to a high one, and the atom must swallow a photon of just that energy. The fixed orbits set the fixed energy levels, the staircase made real, and the jumps between them produced the sharp lines of colour. The test was merciless and immediate. If Bohr's allowed orbits were right, then the energy gaps between them should produce light of exactly the colours hydrogen actually gives off. He did the calculation, working out the energies of his permitted orbits and the gaps between them, and out came the precise positions of the hydrogen lines, the very ones Balmer the schoolteacher had fit by guesswork 30 years earlier. Bohr's forbidden orbits reproduced the real spectrum of hydrogen, line for line, with no fudging. The strange decree predicted reality to the digit. It worked. Here is the everyday handle for what Bohr did. Picture a child on a swing who, by some rule of this odd playground, is allowed to swing only at certain fixed heights and at no others. The child can swing gently at the lowest allowed height, or be given a push-up to the next allowed height, or the next, but can never hover at any height in between. To rise, the child must absorb exactly the right push to reach the next allowed level, no more and no less. To drop, the child must release exactly the energy of one level. The allowed heights are Bohr's orbits. The pushes given and released are the photons. The in-between heights simply do not exist for this swing, so Bohr had saved the atom, at least on paper, by the brute force of a rule he could not justify. The electron does not collapse because it is forbidden to. It gives off only certain colours because it can only sit on certain rungs and only jump between them. The matter-of-fact strangeness of this should not be lost. A young man simply told the electron what it was allowed to do, and the universe agreed. But a rule that works without a reason is a debt that has to be paid. Before we ask why the orbits are allowed, we should look at the most important orbit of all, the lowest one, because that lowest rung is where the answer to our whole question begins to take shape. Among Bohr's allowed orbits, one stands apart, and it is the one that matters most for our question. It is the lowest one, the orbit closest to the nucleus, the rung beneath which there are no more rungs. Bohr called it, and we still call it, the ground state. It is the floor of the atom. An electron in the ground state is in the lowest energy it is allowed to have, sitting on the bottom step of the staircase, And here is the crucial part. From the ground state, there is nowhere lower to go. This single feature is what finally answers the death spiral crisis, and it does so cleanly. Recall the catastrophe. The classical electron should radiate away its energy and spiral down into the nucleus in 16 trillionths of a second. But in Bohr's atom, the electron in the ground state cannot spiral inward, because spiraling inward would mean dropping to a lower energy, and there is no lower energy to drop to. The ground state is the bottom. The staircase simply ends there, with no step beneath it. The electron sits on that lowest rung and stays, because falling further is not an option the universe offers. Think of what this resolves. The whole disaster of the classical atom was the endless fall, the electron forever losing energy and forever sinking closer to the centre. The ground state puts a hard floor under that fall. The electron can give off light and drop, yes, but only down to the ground state, and then it stops, because below the floor there is nothing. It is like a ball bouncing down a staircase that finally reaches the bottom step and comes to rest, not because it ran out of energy in the old sense, but because there is no further step for it to fall onto. The bouncing ends at the floor. Here is the everyday handle, and it is worth holding carefully. Imagine a marble rolling around inside a smooth, round bowl. Set it rolling high up the side, and it circles down toward the bottom, round and round, losing height. But once it reaches the very bottom of the bowl, it can go no lower. It can still be moving, still have energy, but it cannot sink any further, because the bottom of the bowl is the bottom. The ground state is the bottom of the bowl. The electron settles there and stays, with energy still in it, but with no lower place to fall. And that last phrase is the seed of our whole answer, so let it register. The electron in the ground state is not motionless. It is not sitting frozen and dead at the lowest rung with nothing happening. It still has energy, a definite, specific, non-zero amount of energy, even at the very bottom. The floor of the atom is not at zero. It sits above zero, and the electron resting on that floor still carries a real quantity of energy that it never gives up, because there is no lower state for that energy to drain into. This is the energy that has been puzzling us from the start. The energy the electron seems to have for free, the energy it holds for billions of years without a source refilling it. So the question we began with has narrowed to something very precise. It is no longer the loose puzzle of why electrons in general have energy. It is this. Why does the ground state, the lowest possible rung, sit above zero rather than at zero? Why does the electron at the very bottom, with nowhere lower to fall, still carry a fixed amount of energy that it cannot give away? Bohr's model tells us the floor exists and even tells us how high above zero it sits, with a real number we can compute, but it does not tell us why. To get closer, we should look at that number itself, the actual size of the ground state energy, and the constant of nature that fixes it. Let us put a real value on the floor of the atom, because the number itself is part of the wonder. For a hydrogen atom in its ground state, the lowest rung, the energy holding the electron to the proton has a definite size. Measured in the units physicists use for single atoms called electron volts, the ground state energy is about 13.6 electron volts. That is the depth of the well. To tear the electron completely free of the proton, to lift it off the bottom rung and out of the atom entirely, you must supply exactly that much energy, 13.6 electron volts, and not a bit less. An electron volt is a tiny amount of energy by human standards. The energy a single electron picks up crossing the small voltage of a flashlight battery. 13.6 of them is still minuscule on the scale of anything you can feel. Yet that small exact number is one of the most important quantities in nature, because it sets the strength of every bond in chemistry, the energy it takes to rearrange atoms, the colours that gases glow. Multiply out across the countless atoms in ordinary matter, and you get the energy of fire, of food, of every chemical change that runs your body and your world. The whole of chemistry lives at the scale of a few electron volts, and hydrogen's 13.6 is the keystone. Where does that exact value come from? It is built out of a few of the deepest constants in physics, fixed numbers woven into the fabric of the world, locked together in one combination. The mass of the electron is in there, that featherweight we struggled to picture earlier. The charge of the electron is in there, its single fixed unit. The speed of light is in there, and Planck's constant is in there, the size of the fundamental lump, the number that rules everything small. Bohr found that these constants combine in one particular way to give the ground state energy, and the answer they produce matches the measured 13.6 to as many decimal places as anyone cares to check. Out of that same combination falls another number, the actual size of the atom, the radius of that lowest orbit. It is called the Bohr radius, and it is about half of 1/10,000,000,000th of a metre. Written differently, you could lay about 5 billion hydrogen atoms side by side across the width of your smallest fingernail. This is why atoms are the size they are, why matter has the density it has, why your hand is the size it is rather than 10 times larger or smaller. The same handful of constants that set the energy of the floor also set the size of the atom, and through it the scale of the solid world. Here is the everyday handle. Think of how the length of a pendulum sets the exact rhythm of a clock. Choose the length, and the swing time is fixed, not by chance but by the unchanging pull of gravity acting on that length. You cannot have a pendulum of that length tick at any other rate. In the same way, the constants of nature fix the energy and size of the atom. Given the mass and charge of the electron, given Planck's constant and the speed of light, the ground state energy of hydrogen can only be 13.6 electron volts, and the atom can only be the size it is. The numbers are not chosen, they fall out, forced from the constants of the world. So we have the floor, and we have its exact height above zero, built from the bedrock constants of nature. Bohr's model gives us all of this, and it gives it beautifully, matching experiment to many digits. It feels like a triumph, and it was. But a triumph built on a rule with no reason is a strange and unstable thing. Bohr's whole edifice rested on a decree he could not explain, and even as it succeeded, its cracks were showing. We need to be honest now about what Bohr's model got right, and, just as importantly, what it could not do at all. It is only fair to take the measure of Bohr's achievement before we find its limits, because the achievement was real and large. He had taken an atom that classical physics said should self-destruct in a flicker and made it stable. He had explained, for the first time, why hydrogen glows in those exact sharp colours and no others, matching the measured lines to stunning precision. He had given the atom a definite size and a definite ground state energy, both built from the fundamental constants of nature. For a single bold idea written down by a young man in 1913, it was an extraordinary leap, and it won Bohr the Nobel Prize and changed physics forever. But press on the model, and it begins to fail, and the failures are not small. The first and deepest is the one we already named. Bohr never explained why the orbits were special. He simply declared that certain orbits were allowed, and the electron in them would not radiate, in flat defiance of Maxwell's settled rule. He gave a recipe for which orbits, a condition the allowed orbits had to satisfy, but no reason why nature should obey that condition. The rule worked, and no one knew why it worked. It sat in the theory like a law handed down without justification, obeyed, but not understood. The second failure showed up the moment anyone tried to use Bohr's model on an atom more complicated than hydrogen. Hydrogen, with its single electron, the model handled triumphantly. But helium, with 2 electrons, it could not handle at all. The neat orbits and tidy energy levels that worked so well for 1 electron fell apart for 2, giving answers that did not match the measured spectrum. Every atom heavier than hydrogen defied the model. A theory that explains only the very simplest case, and breaks on the second simplest, is telling you that it has caught a piece of the truth, but not the truth itself. There were finer failures too. When physicists looked very closely at the hydrogen lines with better instruments, they found that some of the single lines were actually split into several lines lying very close together. a fine structure the simple Bohr model did not predict. The model also said nothing about how bright each line should be, why some spectral lines blaze and others are faint. It treated the electron as a little ball on a definite track, a planet on a wire, and that picture, for all its success with hydrogen's energies, was clearly too crude to hold the full behaviour of the atom. Here is the honest everyday handle for where Bohr stood. Imagine someone who has never seen the sea works out. From a single tide chart for one harbour, a rule that predicts the high and low tides there with perfect accuracy. The rule is real, it works, it is a genuine discovery. But it says nothing about why the tides happen, and it fails completely at the next harbour down the coast, where the pattern is different. You would rightly conclude that the person had found a true shadow of something deeper, the pull of the moon, without yet grasping the thing casting the shadow. Bohr had the tide chart of hydrogen. He did not yet have the moon. So Bohr's atom was a brilliant, lucky, incomplete sketch, a model that captured the energy levels of hydrogen by a rule it could not justify and could not extend. The physics was clearly pointing at something deeper underneath, some reason the orbits had to be what they were, some truth that would explain the rule rather than just assert it. That deeper truth arrived from an utterly unexpected direction, from a French aristocrat with a wild idea about what the electron really is. He suggested that the electron is not a little ball at all, but something that ripples, and that single thought cracked the whole problem open. The idea that broke the logjam came from a French physicist named Louis de Broglie, a member of an old aristocratic family who had come to physics late, after first studying history. In 1924, in his doctoral thesis, he made a suggestion so strange that his examiners did not know what to make of it, and reportedly asked Einstein whether it was nonsense. Einstein said it was not nonsense. De Broglie's thought was this: physicists had recently been forced to accept that light, long thought to be a pure wave, also behaves like a stream of particles, the photons of Einstein. De Broglie asked the mirror question: if a wave can act like a particle, might a particle act like a wave? In particular, might the electron, that tiny point of mass and charge we have been treating as a little ball, actually be a wave as well? Might it ripple? De Broglie put real mathematics behind the idea, proposing that every particle has a wavelength tied to its motion, with faster, heavier particles having shorter wavelengths and slower, lighter ones having longer waves. For everyday objects, the wavelength he predicted is so absurdly small that it is utterly undetectable, which is why a thrown baseball never shows any rippling. But for something as light as an electron, the predicted wavelength is comparable to the size of an atom, exactly the scale where it might matter. At first this was pure speculation, a beautiful symmetry with no proof, but within a few years it was tested and confirmed, and the confirmation was direct. Two American physicists, Clinton Davison and Lester Germer, working at a laboratory in New York, fired a beam of electrons at a crystal and found that the electrons came off in a pattern of peaks and troughs, bunching at some angles and vanishing at others. That pattern is the unmistakable signature of waves. Waves do this when they overlap, reinforcing where crests meet crests and cancelling where crests meet troughs. Particles treated as little balls do not. The electrons were rippling, and the ripples were interfering just as de Broglie had dared to predict. Here is the everyday handle, and it is worth sitting with, because the idea is genuinely hard. Drop 2 stones into a still pond a little apart, and the ripples spread out from each and cross. Where 2 crests meet, the water humps up higher. Where a crest meets a trough, the water flattens to stillness. The result is a pattern of stronger and calmer patches across the surface, a fixed design made purely by waves overlapping. When electrons fired at a crystal produce exactly this kind of pattern, of more and less, of bunched and bare, it can only mean the electrons are spreading and overlapping like the ripples on the pond. The electron is not a tiny pellet flying a single path. It is something that spreads. This is one of the strangest truths in all of physics, and the calm thing to do is to say it plainly and let it stand. The electron is not a little ball, and it is not purely a wave either. It is something that has no good everyday name, that behaves like a spread-out ripple when it travels and like a concentrated point when it is caught and measured. We call this wave-particle duality, but the name is just a label for our surprise. The real lesson is that the electron is a different kind of thing than anything in your daily experience, and the Bohr picture we have been leaning on, the planet on its orbit, was always an approximation to something far more fluid. And here is why this cracks Bohr's problem open. If the electron is a wave, then asking it to circle the nucleus is asking a wave to wrap around a loop. And waves wrapped around loops can only do certain things, can only fit in certain ways for reasons you can see and feel. The mysterious allowed orbits that Bohr had to decree, the rule with no reason, suddenly have a reason waiting in the wave. We only have to ask what it means for a wave to fit neatly around the nucleus, and the forbidden orbits stop being forbidden by decree and start being the only orbits a wave can hold. To see why a wave can only wrap a loop in certain ways, start with something you can hear. Pluck a guitar string, and it sounds a definite note, a clean pitch, not a smear of every pitch at once. The reason is that the string is tied down at both ends, and a wave trapped between two fixed ends can only vibrate in certain neat patterns, the ones that fit the length of the string exactly. The lowest pattern is a single arc, the whole string bowing up and down together. The next is 2 arcs, then 3, always a whole number of arcs fitting between the fixed ends. A pattern with 2.5 arcs cannot exist on that string, because the ends are pinned and a fractional pattern would not meet them cleanly. The allowed notes are the patterns that fit. These neat fitting patterns are called standing waves, because they do not travel along the string, they sit in place, vibrating. A standing wave is what you get when a wave is confined and must close on itself, or meet its boundaries exactly. The key feature, the one that matters for the atom, is that confinement allows only whole number patterns. 1 arc, 2 arcs, 3 arcs, never a fraction. The wholeness is forced by the geometry. There is no way to fit 2.5 waves into a space that demands the pattern close up neatly, just as there is no way to lay a whole number of identical tiles across a gap unless they happen to fit. Now take that idea off the straight string and wrap it around a circle. Imagine the electron as a wave looped around the nucleus. For the wave to be stable, to hold its shape as it goes around, it must meet itself cleanly when it comes back to its starting point, crest joining smoothly to crest. That can only happen if a whole number of the electron's wavelengths fit exactly around the loop. 1 full wavelength around, or 2, or 3, but never 2.5. If a fractional number of wavelengths tried to close the loop, the wave would come back out of step with itself, crest landing on trough, and it would cancel itself out and cease to be. Only the whole number loops survive. There it is. That is Bohr's mysterious rule. No longer a decree but a consequence. The special allowed orbits are exactly the ones where a whole number of electron wavelengths fits neatly around the circle. The orbits in between are forbidden not because anyone forbade them, but because a wave simply cannot hold a stable shape there, cannot close on itself, and so cannot exist. When de Broglie's wavelength is put into this fitting condition, it produces precisely the allowed orbits Bohr had to assume. The rule with no reason now has its reason. The electron's orbits are quantized because the electron is a wave, and a wave wrapped on a loop can only be whole. Here is the everyday handle drawn tight. Think of a circular running track and a line of identical floor tiles you want to lay all the way around it, end to end, so the last tile meets the first with no gap and no overlap. This only works if the tiles happen to fit a whole number of times around the track. If they do not, the last tile collides with the first or leaves a gap, and the ring will not close. The electron wave is the line of tiles. The orbits that work are the ones where the wave closes perfectly on itself, a whole number of wavelengths around. The mismatched orbits cannot close, so the electron cannot live there. This was a profound relief and a deeper mystery at once. The allowed energies of the atom came from a wave fitting around a loop, which was beautiful and made sense. But it also meant the old picture of the electron as a tidy ball on a track was finished for good. If the electron is a spread-out wave, then it is not really at any one place on the loop at all. It is smeared around it. And that raises a hard new question. If the electron is not a point on an orbit but a wave spread through space, then where exactly is it? The answer, when it came, dissolved the orbit entirely and replaced it with something far stranger, a cloud. The man who turned de Broglie's loops into a full theory was an Austrian physicist named Erwin Schrödinger, who worked out his central idea over the Christmas holiday of 1925, reportedly at a mountain villa in the Alps, away from the distractions of home. He took the notion that the electron is a wave and wrote down an equation, now named for him, that describes how that wave is shaped and how it changes. Schrödinger's equation is to the quantum world what Newton's laws were to the world of planets and projectiles, the central machine that takes a situation and tells you how the wave behaves. Feed it the pull of the nucleus, and it gives you the exact shape of the electron's wave around it, and the exact energies allowed. But Schrödinger's equation raised a sharp question that he himself could not answer at first. The equation gave a wave, spread out through the space around the nucleus. A wave of what exactly? For a sound wave, the thing waving is air pressure. For a water wave, it is the height of the water. What was waving in the electron's wave? Schrödinger first hoped the wave was the electron itself. The electron literally smeared out into a cloud of charge. But that did not quite work, because whenever you actually catch an electron, you catch a whole one at a single spot, never a smeared fraction of one spread across a region. The answer came from a German physicist named Max Born, and it is one of the most important and unsettling ideas in all of science. Born proposed that the electron's wave is not a wave of charge or stuff, but a wave of probability. Where the wave is large, the electron is likely to be found. Where the wave is small, the electron is unlikely to be found. Where the wave is zero, the electron is never found. The wave does not tell you where the electron is. It tells you the odds of finding it at each place, if you go looking. The electron between measurements does not have a single definite position at all. It has a spread of possibilities, and the wave is the map of those odds. This replaces Bohr's clean orbit with something far stranger and truer, called an orbital, or more vividly a probability cloud. The electron in a hydrogen atom is not circling the nucleus on a track. It is spread around it as a cloud of likelihood, denser where it is more likely to be found, and thinner where it is less likely, a soft three-dimensional haze surrounding the central proton. For the ground state of hydrogen, this cloud is a simple round ball, thickest near the nucleus, and fading smoothly outward in all directions, with no edge, just a gentle thinning into near nothing far away. Here is the everyday handle. Picture a fast ceiling fan with its blades spinning. While the blades whirl, you cannot point to where a single blade is at this instant. Instead, you see a soft, continuous disk, a blur where the blade probably is at any moment, denser and fainter in places depending on how the blade spends its time. The electron cloud is like that blur, except it is not made of a fast-moving blade we simply cannot track. The electron genuinely does not have a single location between measurements. The cloud is not our ignorance of a hidden position. The cloud is the whole truth of where the electron is, which is to say spread out, everywhere the cloud is thick, all at once. So the orbit is gone, dissolved into a cloud of pure probability, and with it goes the last trace of the little planet picture we started with. The electron is a standing wave of likelihood wrapped around the nucleus, holding a definite energy but no definite place. And this strange new picture, a thing with energy but no fixed position, sits right next to the deepest limit in all of physics, a hard rule about how much we're even allowed to know about the electron at once. That rule is the next piece, and it carries us close to the heart of where the electron's energy truly comes from. The hard limit on what we can know about the electron was found by a young German physicist named Werner Heisenberg, who was only in his mid-20s when he reshaped physics, and who worked out a key part of his thinking while recovering from terrible hay fever on a barren, nearly pollen-free North Sea island called Helgoland. In 1927, he stated a principle that sounds at first like a statement about clumsy measuring, but is in fact a statement about the deep nature of the electron itself. It is called the uncertainty principle, and it sets a floor below which knowledge cannot go. The principle concerns two things about the electron: its position and its momentum. Position is simply where it is. Momentum is a measure of its motion, how fast it is going and in what direction, scaled by its mass. Heisenberg found that these two quantities are locked together in a strange trade. The more precisely you pin down the electron's position, the more uncertain its momentum becomes, and the more precisely you pin down its momentum, the more uncertain its position becomes. You can know one sharply, or the other sharply, but never both at once. There is a hard limit set by Planck's constant again on how small the two uncertainties can be together. It is vital to understand what kind of limit this is, because it is easy to get wrong. This is not a matter of clumsy instruments or careless technique. It is not that we lack the skill to measure both at once and might do better with finer tools. The uncertainty is woven into what the electron is. An electron with a perfectly definite position simply does not have a definite momentum, not hidden from us, but genuinely undefined. The trade is a feature of the wave nature we have been building toward. A wave squeezed into a tiny region must be made of many different wavelengths jumbled together, and since wavelength is tied to momentum, a sharply located wave has a spread out, uncertain motion built in. Here is the everyday handle drawn from sound, which is also made of waves. Imagine a very short, sharp click, a sound that happens at one crisp instant. Because it is so brief, so well located in time, it has no clear pitch. You cannot hum it, because it is too short to carry a definite note. Now imagine a long, sustained musical tone, a single clear pitch held for many seconds. It has a definite pitch precisely because it lasts a long time, and is spread out in time, not located at any one instant. You can have a sound sharply located in time, or a sound with a sharply defined pitch, but not both. Location in time and definiteness of pitch trade against each other, exactly as position and momentum do for the electron. This trade is not a small technical footnote. It is one of the load-bearing walls of reality, and it bears directly on our question. The electron in the atom is confined, held in close to the nucleus by the electric pull, squeezed into the tiny region of the atom, around a 10/1000th of a meter across. By the uncertainty principle, an electron squeezed into so small a space, so sharply located, cannot have a small settled momentum. Confining it to a small region forces its motion to be large and uncertain. The tighter you trap it, the more it is forced to move, and a thing that is forced to move has energy of motion. We are now one step from the answer. Let us draw out the consequence carefully, because this is the hinge of the whole story. The uncertainty principle says that pinning a particle into a small region forces its momentum to be large and unsettled. Squeeze the space the electron can occupy, and you drive up the spread of its motion. The electron in the atom is squeezed, held near the nucleus by the electric pull, confined to that tiny 10/1000th of a meter region. Therefore the electron is forced to have motion, forced to carry energy of motion, simply because it is confined. The confinement itself manufactures the energy. The trapping and the moving are two faces of one fact. This is a genuinely new kind of answer, unlike anything in the everyday world, so let us be careful and slow with it. In ordinary life, you can trap a thing and have it sit perfectly still. Put a marble in a bowl, and it rolls to the bottom and stops, motionless, resting. Trap a ball in a box, and it can lie on the floor of the box, dead still, going nowhere. Confinement in your daily experience does not force motion. A trapped thing can be a still thing. This is so obvious that it never needs saying, and it is exactly the intuition the quantum world overturns. For the electron, confinement and stillness cannot coexist. If the electron were to sit perfectly still at one definite spot, It would have both a definite position, the spot, and a definite momentum, namely 0. But the uncertainty principle forbids exactly that pairing. A definite position with a definite settled momentum of 0 is the one thing the electron is not allowed to have. So the electron cannot do what the marble does. It cannot settle to the bottom and stop. The very act of being held in a small region forbids it from being still, because stillness in a known place is the forbidden combination. The electron must keep moving, must keep carrying energy of motion, because the alternative is not permitted by the structure of the world. Here is the everyday handle, as close as the everyday can come. Imagine a tiny, restless creature you're trying to hold cupped in your two hands. The tighter you close your hands around it, the smaller the space you leave it, the more frantically it darts and pushes against your palms, never resting. Loosen your grip and give it room, and it calms and moves less. Squeeze it into almost no space, and its motion becomes wild. The electron is like that creature, except its restlessness is not a creature's will. It is a law. The smaller the space it is forced into, the more motion the universe requires it to have, with no choice in the matter and no way to calm it. So the electron in the atom, confined near the nucleus, is forced by the deepest rule of the quantum world to carry energy of motion. It cannot be still, and because it cannot be still, it always has this energy, with no need for anything to give it. The energy is the unavoidable price of being a confined wave. This forced, irreducible motion, the motion that confinement demands and that nothing can remove, has a name. It is called zero-point energy, and it is one of the most beautiful and strange ideas in all of physics, the still center where our long question finally begins to find its answer. The restless motion that confinement forces on the electron has a name, and the name carries its strangeness in plain words. It is called zero-point energy. The 0 point refers to temperature and to the coldest condition that can ever exist, called absolute zero. Absolute zero sits at about minus 273 degrees on the Celsius scale, and it is the true bottom of cold, the point where you have removed every last bit of heat that can be removed. Everywhere in the everyday world, when you cool a thing toward absolute zero, its motion fades. Atoms that jiggle with warmth grow still as the heat leaves. The colder it gets, the quieter the jiggling, and you would expect that at the very bottom, at absolute zero itself, all motion would stop completely. Everything would be frozen, perfectly, utterly still. That is exactly what does not happen. Cool the electron in an atom all the way down to absolute zero, take away every scrap of heat there is to take, and it still moves. It still carries energy of motion, the same forced motion the uncertainty principle demands of a confined wave. This leftover motion is the 0 point energy, the energy that remains when all the energy that can be removed has been removed. It is the motion you cannot cool away, because it was never heat in the first place. It is built into what the electron is when it is held in a small space, and no amount of cooling can touch it. This is not a fragile idea seen only in equations. It shows itself in the real world in a way you could put in a bottle. Take helium, the light gas that fills party balloons, and cool it down toward absolute zero. Every other substance cooled far enough freezes into a solid. Water becomes ice, air becomes frost, metals grow rigid. But helium, at ordinary pressure, never freezes solid no matter how cold you make it, not even at absolute zero. It stays a liquid forever. The reason is 0 point energy. The helium atoms are so light and confined so closely by their neighbours that their forced 0 point motion keeps them jiggling against each other hard enough to prevent them ever locking into a solid. The liquid that will not freeze is 0 point energy you can see. Here is the everyday handle, and it pushes against everything ordinary life has taught you. Imagine a child's swing that, however long you wait, will not come fully to rest. You stop pushing, and friction slows it, and it swings smaller and smaller, and in the ordinary world it finally hangs dead still. But this swing, when it reaches the smallest swing, it is allowed. simply keeps swinging at that smallest size forever, never hanging straight down, never fully still, because the rules of its strange playground forbid perfect rest. There is a smallest motion it must always have. The electron in its ground state is that swing. It has swung down to its smallest allowed motion, and there it stays, moving, because complete stillness is the one state the world will not let it occupy. So the deepest floor of the atom is not a place of rest. It is a place of permanent, irreducible motion, the quietest the electron can ever be, and yet still moving, still carrying energy, forever. The electron in the ground state has been doing this since the atom formed, and it will keep doing it for as long as the atom exists, with nothing to feed it and nothing able to stop it. We have found, at last, the source of the energy that puzzled us at the very start, the energy the electron seems to have for free. It does not come from anywhere. It was never given. It is the unavoidable price of being a confined wave, and that answer deserves to be stated plainly on its own. Let us say the first real answer cleanly, now that we have built the ground to hold it. The energy of the electron in the ground state of the atom was never given to it by anything. No source supplied it. No process delivered it. There was no moment when energy flowed into the electron to set it moving. The motion of the electron in its lowest state is not borrowed from a battery, or a star, or any outside hand. It is simply what an electron is when it is confined to the small space of an atom. The energy is structural. It belongs to the situation itself, to the fact of a wave held in a small region, and it would be there whether or not anything ever put it there. This is why the electron never runs down, and why the question that nearly broke physics has a calm answer at its centre. A spinning top slows because friction drains its motion away into heat, into the table, into the air. The motion leaks out to somewhere lower. But the electron in the ground state has nowhere lower to leak to. It is already at the bottom rung, and the bottom rung is not at zero, because the uncertainty principle holds it above zero. There is no lower state for its energy to drain into, so it cannot drain. The electron keeps its zero-point motion not because something keeps refilling it, but because nothing can carry it away. Conservation of energy is not violated. There is simply no path for the energy to leave. Hold the two halves of this together, because together they dissolve the original worry completely. The energy was never given, so we do not need to find a source for it. And the energy cannot leave, so we do not need to explain why it has not run out. The puzzle assumed the electron's energy was like the energy of a thrown ball or a wound spring, something supplied from outside that ought to deplete. The truth is that the ground state energy is more like the roundness of a circle, a property of the thing's very shape, not fuel poured into it. A circle does not use up its roundness by being round. The electron does not use up its zero-point energy by moving. Here is the everyday handle as close as the ordinary can reach. Think of the depth of the deepest valley on a landscape. The valley floor sits at a certain height, and a stream that flows down into it gathers there and can go no lower, because there is no lower ground for it to run to. The water does not need to be refilled to stay in the valley. It stays because it has reached the bottom, and the bottom is where it rests. The electron's ground state energy is the height of that valley floor set by the shape of the land, which here is the shape of the atom and the rules of the quantum world. It rests there because there is nowhere lower, and it needs no source because it was the shape of things all along. So one whole layer of our question is answered, and answered honestly. Where does the electron in the atom get the energy it never loses? It does not get it. The energy is the built-in cost of being a confined wave, held above zero by the uncertainty principle, unable to leave because nothing lies below it. That is the deepest answer for the electron bound in its atom. But the electron carries another, even larger store of energy, one that has nothing to do with confinement or orbits, one it would hold even drifting alone in empty space. That energy is locked inside its mass, and to see it we turn to the most famous equation ever written. Strip the electron of everything, take it out of the atom, away from every nucleus and every other particle, and set it alone and motionless in the emptiness of space, as still as the rules allow. With no orbit, no confinement, no motion to speak of, you might think it now holds no energy at all. It does. Even a single electron alone and at rest carries a large store of energy simply because it has mass. This is the rest mass energy, and it comes from the most famous equation in all of science, written by Einstein in 1905, the relation that energy equals mass times the speed of light squared. That little equation says something staggering and exact. Mass and energy are not two separate things that happen to be related. They are the same thing, measured in different ways, and you can convert one into the other. A small amount of mass is equal to a large amount of energy, because the conversion runs through the speed of light multiplied by itself, and the speed of light is an enormous number, about 300 million meters every second. Squaring it gives a number larger still, so even the featherweight mass of an electron, that decimal point and 30 zeros and a 9, becomes a meaningful packet of energy once multiplied by that vast factor, vast. For the electron, the rest mass energy works out to about 511,000 electron volts. Set that beside the 13.6 electron volts that binds the electron in hydrogen, and the difference is staggering. The energy locked in the electron's mass is roughly 40,000 times larger than the energy holding it in the atom. The binding energy we spent so long chasing, the whole drama of orbits and the ground state, is a tiny ripple riding on top of a vast silent ocean of energy that the electron carries just by existing. The mass itself is the larger store by far. This is not a calculation that only lives on paper. It is confirmed every day, directly and violently. An electron has a mirror twin, a particle of the same mass but opposite charge, which we will meet properly in a moment. When an electron meets that twin, the two of them vanish completely, their entire mass converting into pure light, into two photons that fly off carrying exactly the energy the equation predicts, 511,000 electron volts apiece. The mass does not break into smaller pieces. It is gone, turned wholly into energy, and the energy that emerges matches Einstein's relation to as fine a measurement as we can make. Medical scanners in hospitals use this exact conversion to see inside the human body, reading the light that flares when electrons meet their twins. Here is the everyday handle. Think of mass as energy in frozen, folded form, the way a tightly wound spring holds the energy of your efforts silently, ready to release. The spring sitting on the table looks inert, holding nothing, yet the energy is in there, locked in its tension, and you feel it the instant the spring is freed. The electron's mass is energy folded up like that spring, except folded far more tightly, by the factor of the speed of light squared. Unfold it by letting the electron meet its twin, and all that energy springs out at once as light. So the electron carries two very different stores of energy. The small one comes from being confined in an atom, the zero-point energy we have already traced. The vast one comes from its mass, present whether it is bound or free, locked in by the most famous equation in physics. To understand where that mass energy itself comes from, we have to let go of the picture of the electron as a particle at all, and meet the deeper thing underneath it, the field. We have called the electron a particle, then a wave, then a cloud of probability, and each picture caught part of the truth and missed part. The deepest picture we have, the one that underlies all the others, sets the lone electron aside and starts somewhere stranger. It says that filling all of space, everywhere, in every cubic inch of the room you sit in, and every reach of empty space between the stars, there is something called the electron field. Not the electrons themselves, but a field, an invisible presence spread through the entire universe, the same way a still pond surface is spread across its whole basin, even where nothing disturbs it. An electron, in this picture, is not a tiny independent object that happens to exist. It is a ripple in that field, a place where the electron field is excited, humped up into a stable little knot of vibration. Where the field is calm and flat, there is no electron. Where the field is stirred into one of its smallest stable ripples, there is one electron. Stir up 2 such ripples, and there are 2 electrons, and because they are all ripples in the one same field, every electron in the universe is identical to every other, exactly the same mass, exactly the same charge with no variation at all. That perfect sameness, which we noted long ago as a deep fact, is explained at last. Electrons are all alike because they are all ripples in a single shared field, like identical waves on one sea. This is the framework called quantum field theory, and it is the most successful description of nature ever built, tested to a precision unmatched anywhere in science. In it, every kind of fundamental particle is a ripple in its own field. There is an electron field whose ripples are electrons. There is a field for light, whose ripples are the photons we met earlier. There are fields for the particles inside the nucleus. The whole universe, in this view, is a set of fields layered through all of space, and everything that exists, all matter and all light, is the patterns of ripples moving across them. Here is the everyday handle. Picture the surface of a vast, calm ocean that covers everything, reaching into every corner of space. Most of it lies flat and quiet, and where it is flat there is nothing to see. But here and there, stable little swells rise up and travel along, holding their shape as they go. Each swell is a particle. An electron is one particular kind of swell on one particular ocean, the electron ocean, and it carries its mass and charge as features of that swell. The ocean is everywhere, even where it is flat and empty. The particle is just the place where the ocean is heaped up into a lasting ripple. This reframing changes what our whole question even means, and it is worth feeling the shift. We have been asking where the electron gets its energy, as if the electron were a thing in itself that needed feeding. But if the electron is a ripple in a field, then its energy is the energy of that ripple, the energy it takes to lift the field into that stable hump and keep it humped. The mass energy locked in the electron is the energy of the standing ripple in the electron field. The electron does not hold energy the way a cup holds water. It is energy, shaped into a lasting disturbance of a field that fills the world. And once you see the electron as a ripple in a field, a question follows that the field itself answers in a way no one expected. If the field can be stirred up into an electron, what happens when you stir it the opposite way? The man who first wrote the equation for the electron field found a second kind of ripple hiding inside his own mathematics, a mirror twin to the electron that no one had ever seen. The equation for the electron field was written in 1928 by an English physicist named Paul Dirac, one of the strangest and most precise minds in the history of science. Dirac was famously silent, so sparing with words that colleagues half-joked his vocabulary held about 1 word per hour, and so literal that he seemed puzzled by ordinary figures of speech. He set out to write an equation for the electron that would respect both the quantum world and Einstein's relativity at once, and after long effort he found it, an equation of rare beauty that described the electron perfectly. But the equation said more than he had asked it to. It had 2 sets of solutions, not one. One set described the ordinary electron, the other set described something that did not yet exist, a particle with the same mass as the electron but the opposite charge, a positive electron. Dirac could have dismissed the extra solutions as a meaningless quirk of the math, and at first the strangeness troubled him. But he trusted his equation more than his expectations, and he took the bold step of believing what it told him. He predicted that there should be a real particle out there, a mirror twin of the electron, identical in mass but carrying positive charge instead of negative. This was the first prediction of what we now call antimatter, a whole shadow category of particles, each the mirror of an ordinary one conjured not from observation, but from the demand that an equation be taken seriously. The prediction was confirmed within a few years. In 1932, an American physicist named Carl Anderson, studying the showers of particles that rained down on Earth from space, found a track in his detector that curved the wrong way, exactly as a positive electron would. He had photographed Dirac's mirror twin, and it was given the name positron. A particle that had existed first only as a second solution in a young man's equation was now caught on film, real, falling out of the sky. It was one of the great vindications of the idea that deep mathematics can see further than the eye. Here is the everyday handle. Imagine you are given a single footprint pressed into soft ground and asked to describe the foot that made it. From that one print you could work out not only the foot itself but its mirror, the other foot, which must exist to match it, even though you have not seen it. The 2 feet are mirror images, the same size, the same shape, reversed. Dirac's equation was the footprint. The electron was the foot he could see. The positron was the other foot demanded by the symmetry of the print, found later exactly where the symmetry said it would be. This mirror twin is what lets the electron's mass energy be released, the conversion we met a moment ago. When an electron meets a positron, the 2 ripples in the field cancel each other, the way a crest meeting an exactly matching trough flattens the water to stillness. Their mass does not go anywhere physical. It converts entirely into light, into the 2 photons carrying the rest mass energy outward. Matter and its mirror, brought together, become pure radiation, and the books balance to the last decimal. So the field beneath the electron holds not one kind of ripple but 2, the electron and its opposite, woven together by the structure of Dirac's equation. And once we accept that empty space is full of fields that can ripple into particles and their mirror twins, a deeper unease creeps in. If the fields are everywhere, even where space looks empty, then perhaps empty space is not empty at all. Perhaps it hums with activity we cannot see, and that hum, faint as it is, leaves a fingerprint on the electron itself. Empty space, in the field picture, cannot be truly empty. The fields are still there, spread through every region, and the uncertainty principle that governs the electron governs the fields as well. Just as it forbids the electron from sitting perfectly still in a perfectly known place, it forbids any field from lying perfectly flat and perfectly quiet. A field that was exactly 0 everywhere, perfectly calm, would be a field with a perfectly definite value and a perfectly definite rate of change. And that sharp pairing is the kind the uncertainty principle does not allow. So the fields cannot be perfectly still. Even in the emptiest vacuum they tremble, flickering with a faint, ceaseless quiver called vacuum fluctuations. This means that what we call empty space is quietly alive. Across the whole vacuum the fields are constantly humming, ripples flickering into being and vanishing again too quickly to be caught directly, like the surface of a pond stirred by a wind you cannot feel. These fleeting ripples are sometimes called virtual particles, brief stirrings of the fields that appear and disappear in an instant. They are not steady particles you could collect, but passing tremors, the unavoidable restlessness of fields that the uncertainty principle will not let rest. The vacuum is not a still, dead nothing. It is a humming, flickering sea of activity holding at the lowest level it is allowed, and this humming vacuum touches the electron. An electron sitting in an atom is not alone with its nucleus. It is immersed in the trembling fields of empty space, and those tiny flickers nudge it, jostle it ever so slightly, shifting its energy by a minuscule amount. For a long time no one suspected this, because the shift is so small. But in 1947, an American physicist named Willis Lamb measured the energy levels of hydrogen with such extraordinary care that he found 2 levels, which the simplest theory said should sit at exactly the same energy, were in fact very slightly apart. Something was nudging one of them. That tiny gap, now called the Lamb shift, was the fingerprint of the humming vacuum pressing on the electron, the first hard proof that empty space is not empty. Here is the everyday handle. Imagine a small boat moored in a harbour that looks perfectly calm, its water flat and glassy to the eye. Watch closely though, and the boat is never quite still. It trembles and bobs by the smallest amount, nudged by countless tiny ripples too faint to see, the harbour's restless undertone working on its hull. You could measure the boat's faint quiver and prove the water is alive with motion you cannot otherwise detect. The electron is that boat. The Lamb shift is its faint quiver, and from it we learned that the vacuum around the electron is forever trembling. This deepens our answer in a quiet way. The electron in the atom is not an isolated thing carrying a fixed private store of energy. It is in constant, intimate contact with the fields of all of space, exchanging the faintest whispers of energy with the humming vacuum at every instant. Its energy is woven into the energy of the whole field that fills the universe. The line between the electron and empty space, which once seemed sharp, blurs into a continuous trembling whole, and the same theory that predicts this humming, the same framework of fields and fluctuations, makes another prediction, one so precise that it stands as the most exact agreement between human calculation and physical reality ever achieved. It concerns the electron's own tiny magnetism, and it is worth meeting on its own, because it shows just how deeply, and how rightly, we have come to understand this small restless thing. The electron has a property we have not yet named, and it is one of the strangest. The electron behaves as though it is spinning, carrying a small amount of what physicists call spin, and because it is a spinning electric charge, it acts as a tiny magnet. Every electron is a minuscule bar magnet, with a north and a south, and this is no abstraction. It is why some materials are magnetic at all. In iron, the tiny magnets of countless electrons line up together, and their combined pull is the force that holds a magnet to your refrigerator door. The familiar magnet in your hand is the collective spin of uncountable electrons, all pointing the same way. The strength of the electron's tiny magnetism is a number that theory can predict and experiment can measure, and the comparison between the two is the sharpest test in all of science. The simplest version of the theory gives a clean, round prediction for the strength. But the humming vacuum changes it. All those flickering virtual particles constantly appearing and vanishing around the electron slightly alter its magnetism, nudging the number away from the clean value by a small calculable amount. The full theory of fields, accounting for the trembling vacuum, predicts this corrected number with breathtaking precision, working through layer upon layer of vacuum effects. When physicists calculate the electron's magnetism this way, and then measure it in the laboratory, the two numbers agree to about 12 digits. To grasp what that means, imagine measuring the distance across an entire continent, thousands of miles, and having your calculated answer match the measured one to within the width of a single human hair. That is the level of agreement between the theory of the electron and the real electron. No other prediction in science, in any field, has ever been confirmed to this depth. The humming vacuum, the virtual particles, the whole strange machinery of fields, all of it must be very close to true, because if it were not, this number would not come out right, and it comes out right to 12 places. Here is the everyday handle for why this matters so much. Suppose someone claims to understand a vast and intricate clock they have never opened. You test them by asking what time the clock will read after running untouched for 1,000 years, and they give you an answer down to the second. 1,000 years later, the clock reads exactly what they said, to the second. You would no longer doubt that they truly understood the clock, because no lucky guess survives a test that fine. The electron's magnetism is that test, and our theory passes it to 12 digits. We understand this small, restless particle, in this respect, more deeply than we understand almost anything else in the universe. Sit with what this confirms: the electron's energy, its mass, its magnetism, its restless zero-point motion, its conversation with the humming vacuum. All of it hangs together in one theory that survives the hardest test we can devise. The answer we have been building, that the electron's energy is the energy of a confined ripple in a field that fills all space, trembling against the fields of an active vacuum, is not a loose story. It is checked against reality to a precision that leaves almost no room for it to be wrong. The deep answer to our question is as solid as any knowledge we hold. Now we can come back up from these depths, back to the world of doorknobs and wires, and look at the ordinary everyday ways that electrons gain and lose energy. Because alongside the built-in energy we have traced, electrons are also pushed up and let down all the time, by heat, by light, and by the simple force of a battery. Step back from the deep picture and return to the atom as a staircase of energy levels, with the electron able to sit on the ground floor or climb to higher rungs. Everything we have said about the built-in ground state energy still holds, but on top of that floor, electrons move up and down between levels all the time, and these everyday jumps are where most of the energy you actually use comes and goes. To lift an electron from a lower rung to a higher one, you must give it exactly the energy of the gap. To bring it back down, it releases exactly that energy again. The ordinary world runs on these climbs and drops. There are 3 common ways to push an electron up to a higher rung, and you meet all of them every day. The first is heat. Warmer material and its atoms jostle harder, and the collisions knock electrons up to higher levels. When those electrons drop back down, they release the energy as light, which is why a poker in a fire glows, why a stove element reddens, why anything hot enough begins to shine. The glow of hot things, the very puzzle that started Planck on the path to quanta, is electrons being knocked up by heat and falling back down as light. The second way is light itself. A photon of just the right energy, striking an atom, can be swallowed whole by an electron, lifting it to a higher rung in a single jump. This is the reverse of the light-giving drop, and it is happening in your eye at this moment. The light entering your eye is absorbed by electrons in the molecules of your retina, kicking them up to higher levels, and that kick begins the chain of signals your brain reads as sight. You're reading these words by electrons absorbing photons and climbing. The same swallowing of light by electrons is how a plant captures sunlight, and how a solar panel turns daylight into current. The third way is voltage, a direct electrical push. Connect a source of electrical force across a material, and it shoves on the electrons, driving them to higher energy, and, in a conductor, sending them streaming along as a current. This is what the switch on your wall does. It does not create electrons or fill them with some new substance. It applies a push that lifts electrons to a higher energy and sets the whole crowd moving, and that flowing, energized crowd is the electricity that lights your lamp and warms your kettle. Here is the everyday handle that ties all 3 together. Think of a ball you want to lift onto a shelf. You can knock it up there by throwing other balls at it, which is heat, the jostling of warm atoms. You can have something carry it up in one lift, which is light, a single photon raising the electron in one jump. Or you can push it up a ramp with steady pressure, which is voltage, the constant electrical shove of a battery or a wall socket. In every case, you supply the energy of the gap, and the electron ends up higher than before, holding that supplied energy until it drops back down and gives it away again. So the everyday energy of electrons, the energy in your lights and screens and heaters, is not the mysterious built-in energy of the ground state. It is energy genuinely supplied from outside by heat or light or voltage, lifting electrons up so they can fall back down and do something useful on the way. This is the energy that does deplete, that must be paid for, that your electric bill measures, and the clearest, most familiar source of that push is the one in every flashlight and phone, the battery, where a quiet chemical reaction drives electrons through a wire. A battery is a small, sealed engine that turns chemistry into a steady electrical push, and its working is worth seeing plainly, because it shows exactly where an everyday electron's energy comes from. Inside a battery are 2 different materials, kept apart, each able to take part in a chemical reaction involving electrons. One material wants to give electrons away, the other wants to take them in. Left to touch directly, they would simply react and release their energy as a little heat. The cleverness of a battery is that it separates the 2 and forces any electrons passing between them to take the long way around, out through the wire and your device and back, doing work for you along the way. When you connect a battery into a circuit, the material at the negative end releases electrons, pushed out by the chemical reaction that wants to happen there. Those electrons flow out into the wire, through whatever you have connected, your bulb or your phone, and back into the positive end, where the other material accepts them into its own waiting reaction. The chemical reaction is the source of the push. The energy that drives the electrons around the circuit comes from the rearranging of atoms inside the battery, from chemical bonds breaking and reforming into a lower energy arrangement, releasing energy as they settle. This is the law of conservation of energy doing its ordinary daily work. The chemical energy stored in the battery's materials, the energy held in the particular arrangement of their atoms, is not created or destroyed. It is converted, turned into the energy of moving electrons, which is then converted again into light in the bulb or sound in the speaker or motion in the small motor. Trace the energy back step by step, and it ends in the chemical bonds inside the battery, which were themselves built up by the energy used to manufacture the battery in the first place. When those bonds have all rearranged to their lowest state, the battery is dead, the chemical push exhausted, and the electrons stop flowing. Nothing was used up except the stored chemistry. Here is the everyday handle. Think of a water wheel turned by a stream running downhill. The water at the top of the hill holds energy of position, and as it flows down through the wheel, that energy is handed to the wheel, which turns and does work, grinding grain or pumping water. The battery is the hill, its chemicals the water held up high, full of stored energy. The wire in your device are the channel the water runs through. The electrons are the water, flowing from the high energy arrangement to the low one, turning your device like the wheel as they pass. When all the water is run down, when the chemicals have all reacted, the flow stops, and the hill is flat. So the energy in the electrons running through your phone right now did come from somewhere definite and findable, and it is not mysterious at all. It came from chemical reactions in the battery, from the energy stored in the arrangement of atoms, converted into electron motion, and then into the work your device does. This is the ordinary, depletable, payable energy of electrons, utterly unlike the built-in zero-point energy of the bound electron, and it obeys conservation of energy at every step. The same is true on the grandest scale for the energy in the sunlight that pours over the whole Earth, which is also, at its root, electrons and energy-changing form in the heart of a star. Nearly all the energy that has ever touched your life traces back to one source, the sun, and at the sun's centre, the story is again about energy-changing form on a colossal scale. Deep in the core of the sun, under crushing pressure, and at a temperature of about 15 million degrees, the nuclei of hydrogen atoms are pressed so hard together that they fuse, merging into helium. This fusion is the engine of the sun, and it is another conversion of mass into energy, governed by the same equation of Einstein's we met for the electron. When hydrogen fuses into helium, a tiny fraction of the mass goes missing, converted into energy exactly as the equation demands, and that energy is what makes the sun shine. The amount of mass turned into energy each second is staggering. The sun converts about 4 million tons of its own mass into pure energy every second, and has been doing so for over 4 billion years, with enough fuel to continue for billions more. That energy begins as light and heat born in the core, and it works its way outward over a very long time before streaming off the sun's surface and crossing space to reach us. The sunlight falling on your skin began as mass at the heart of the sun, converted to energy by fusion, the same mass-to-energy conversion that frees the electron's rest energy when it meets its twin. When that sunlight reaches the Earth, electrons take over the story again. The light is absorbed by electrons in the leaves of plants, lifting those electrons to higher energy, exactly the climbing we traced a moment ago. The plants use that captured energy to build sugars, locking the sun's energy into chemical bonds. Animals eat the plants and free that energy to live and move. Buried and compressed over ages, ancient plants became coal and oil, holding the sun's old energy still, which we now burn to push electrons through wires once more. Every campfire, every meal, every tank of fuel is sunlight stored as chemistry and released again, and at each step electrons are the carriers, climbing and falling between their energy levels. Here is the everyday handle. Picture a single great spring, wound up at the centre of the sun by fusion, releasing its tension slowly as light. That light crosses space and wins countless smaller springs here on Earth, the chemical bonds in plants, each holding a little of the sun's energy. Those small springs are unwound when we eat or burn what the plants made, releasing the stored energy to do our work, and the work is done by electrons moving from rung to rung. The sun winds the great spring. Life and machinery unwind the small ones. The energy is the same throughout, only handed from form to form along a very long chain. So the energy in the light you live by, like the energy in your battery, came from somewhere real and traceable, from mass converted into energy in the heart of a star, carried to Earth as light, captured and stored and released by electrons climbing and falling. None of it was made from nothing. All of it was converted form into form with the total always preserved. That preservation, the rule we first met long ago and have leaned on at every step, is the deepest law beneath this entire story, and it deserves to be stated now in its full weight. There is one rule that has stood beneath every answer in this whole account, quietly holding the structure up, and it is time to name it as the bedrock it is. Energy is never created and never destroyed. It only changes from one form into another. We met this law early, in the falling book and the churning paddle, and it has returned at every turn since, in the battery, in the sun, in the electron meeting its twin. It is called the conservation of energy, and as far as we have ever been able to test across every experiment ever performed, it holds without a single exception. It is perhaps the most thoroughly confirmed statement in all of science. Hold this law against our whole journey and see how it shaped every answer. The everyday energy of electrons in wires and lights never appeared from nowhere. It was always converted, from chemical bonds, from sunlight, from mass, each form traceable to the one before. The energy could move, transform and flow, but the total never grew and never shrank. Whenever it seemed that energy was created, a closer look found it converted from some store we had missed. Whenever it seemed destroyed, a closer look found it carried away as heat or light. The books always balance every time down to the finest measurement. This is why the original question carried such force, and why it could not be waved away. If energy is never created, then the electron in the atom, moving for billions of years, cannot be making its own energy from nothing. The law forbids it. Either some source must supply that energy, or the electron must have held it from the very start. There was no third path the law would allow, and the answer we found honours the law exactly. The electron's ground state energy was not created and is not being created. It is the built-in energy of a confined wave, present from the moment the atom formed, never made and never lost, simply held, because there is no lower state for it to fall into, and no process that adds to it. Here is the everyday handle, the plainest way to hold the law. Think of money in a sealed room with no door, only people inside passing coins among themselves. The coins move from hand to hand endlessly, and any one person's pile grows or shrinks, but the total number of coins in the room never changes, because none can enter and none can leave. Energy is like those coins, and the universe is the sealed room. Energy passes from form to form, from mass to motion to light to chemistry and back, but the total in the whole universe stays exactly fixed. No coin is ever made, no coin is ever lost. Every gain somewhere is a loss somewhere else, always, without fail. So conservation of energy is not one fact among many. It is the frame inside which every other answer had to fit, the rule that turned a child's simple question into a demand physics could not dodge. It told us that the electron's energy must come from somewhere or be built in from the start, and by holding us to that, it led us all the way down to the 0-point energy of a confined wave and the rest energy locked in mass. With this law in hand, and with every thread we have gathered, we can finally return to the question we began with and answer it plainly, in the simplest words, the way it deserves. So, where does an electron get its energy from? We have travelled a long way to answer it, and now we can say it simply, in the plain words it always deserved? The answer comes in two parts, because there are two very different kinds of energy an electron carries, and they have two very different sources. The everyday energy, the energy in the spark at the doorknob and the warmth of the phone in your hand, is supplied from outside, and it is fully traceable. It comes from a battery's chemistry, or from sunlight born of fusion in a star, or from the heat of a fire, lifting electrons to higher rungs so they can fall back down and do work for you on the way. This energy obeys conservation of energy at every step, converted from one form to another, never made from nothing, always paid for by some store that empties as it gives. This is the energy that runs down, that your battery loses, that the sun will one day exhaust. There is no mystery in it, only a long chain of conversions you can follow back to its source. But the deeper energy, the energy that puzzled us most, the energy the bound electron holds for billions of years without any source refilling it, was never given to the electron at all. It is the built-in energy of a confined wave. The electron, held in the small space of the atom, cannot be still, because the uncertainty principle forbids a confined thing from resting motionless. So it carries an irreducible zero-point motion, an energy that was never supplied and cannot leak away, because there is no lower state beneath it to drain into. And beneath even that lies the vast energy locked in the electron's mass, the rest energy of a ripple standing in the electron field that fills all of space. The electron does not hold this energy the way a cup holds water. The electron is this energy, shaped into a lasting disturbance of a field, humming against the restless vacuum of empty space. So the honest answer to the question is gentle and strange at once. For the electron bound in its atom, the energy comes from nowhere because it was never given. It is simply what an electron is, a knot of energy in a field, confined and therefore moving, present from the moment the atom formed and lasting as long as the atom lasts. Nothing has to feed it, nothing can wear it out. The thing that nearly broke physics 100 years ago turned out not to be a leak that needed plugging, but a flaw that needed understanding. Now go back to that winter morning and the snap at the doorknob. When the spark jumps to your hand, you're feeling electrons that were forged in stars, carrying mass energy locked in by the structure of the universe, electrons that have never once been still since the atoms that hold them came together and never will be. The same restlessness lives in every atom of your own body, in the carbon and the oxygen and the iron in your blood, each electron humming with energy that was never supplied and will never run out. You are made of these small, tireless ripples, billions of years old, holding their motion through the deepest cold and the longest time, asking nothing from anyone. That is what the electron is, and that is where its energy comes from. Not from a source, but from the shape of the world itself. The next time you feel that small electric snap, you will know that you have touched something that has been moving since before the Earth was born, and that will go on moving, quietly and without end, long after the light here has gone out. The wonder was never far away. It was in your hand the whole time,